Hello everybody, and welcome to this short introduction to elasto-hydrodynamic lubrication. I'm Roland Larsson. I'm from Luleå University of Technology. I will now describe the fundamentals about EHL, and this is the outline. First, I will discuss and explain what EHL is, and then I will describe the mechanisms of EHL and explain why it is working at all, and try to explain why a protecting lubricating film is formed there. And finally, I will also describe what this picture shows. It's a beautiful figure, and I will explain later what that is used to. So, starting with the first question, what is EHL? Well, EHL is, as I said, elasto-hydrodynamic lubrication. It's about lubricating non-conformal surfaces. You may remember from the contact mechanics that you have a non-conformal contact in between, for example, two rollers like this, or like the roller and raceway contact in a roller bearing. So it's a very small contact region, and of that reason we have very high contact pressures. We normally talk about gigapascal levels of pressure there. And since the pressure is high, the surfaces will become elastically deformed. And they should be elastically deformed. They mustn't be plastically deformed, because then you damage the bearing. And since the pressures are high and the contact is small, the lubricant films normally become very thin. They are normally much thinner than 1 micrometer, but that can still be sufficient. And apart from rolling element bearings, you also find EHL in, for example, gears and cam mechanisms. If you compare a non-conformal bearing with a conformal one, like the rolling element bearing here and the journal bearing here, you may think that, okay, a journal bearing with very low contact pressure and also thicker lubricant film here, it should be better from a performance point of view. But actually they have about the same load carrying capacity, and you can think about that. How can that be possible? Stop the video for a while and think about it in a few minutes, and then we will try to explain it in this video. First, I want to describe some different types of EHL. When we talk about machine components, then we normally talk about non-conformal hard EHL, as I already been mentioning the bearings. And this is a hydraulic motor with you can find here a cam mechanism. For example, here is a roller and here is a cam. That's a typical hard EHL contact, non-conformal steel surfaces typically. But you can also find non-conformal soft EHL, like the contact between the tire and the road. That is definitely a deformed contact, and the same goes for a lip sealing contact with a surface. But you may also find EHL in conformal contacts. The pressures can be high enough to deform the surfaces and in such a way that it influences the lubrication itself. This is actually from the same machine here. This is a hydraulic motor, so another part of the machine you can find conformal EHL there. In a hip joint you may find that too, and even in skiing you may find conformal EHL. So I'll discuss a little bit how a film is formed here and why it is formed. Starting with the contact mechanics a little bit and the conformal contact. As we have been discussing already, when you put a cylinder, for example, in contact with a flat surface, then you end up with a very concentrated force and a small contact region. So in this case, at a low load, you have a pressure like this. It's concentrated. It's very narrow contact. If you compare to the radius here, you don't see the full radius of the cylinder here. If you increase the pressure or the load 10 times, you increase the contact too, and if you continue to increase it, you end up with this one, and now you have increased the pressure, but more important, you have increased the contact. So in here, in this part, there is a kind of flattening of the surfaces. So it's more or less a flat contact here. So still with a certain size, so this is all the three different loads, and this is the corresponding pressure distributions. So now you can see here in this case the pressure was half a gigapascal approximately, but if you continue to increase the pressure or the load, then you make it bigger and bigger, and you reach maybe several gigapascals, and the contact width will then grow also very much. So what you form here is a contact which is relatively large. It's maybe just a millimeter or less than a millimeter, but there is a possibility to see it as a flat region to be lubricated. So if this is a dry contact, and you start moving the surfaces, you can see here that you form the wedge you really want for hydrodynamic lubrication. If the two surfaces are rolling, which is the case in a bearing, for example, the surfaces will bring in lubricant into the wedge and then force the surfaces apart due to the pressure formed due to the wedge effect here. So that reason you form a thin film, and it is very thin. It is very much thinner than the length, but it is a typical hydrodynamic film, which is typically much thinner than its length. So this figure shows the typical features of the EHL contact. You have it's a little bit exaggerated here. The size of remember that this contact zone is maybe only 1% of the diameter of the rollers. So, but still, you bring in the lubricant with the motion of the surface here. You form a relatively flat part here, a constant film thickness here, but then you actually find the thinnest part of the film at the very exit of the contact. So here the pressure falls to zero again. And that is the typical feature of EHL contact, and it is followed by a pressure distribution in the lubricant that looks something like this, and it's following the Hertz dry contact pressure very well, apart from here at the inlet where the pressure is built up a little bit before the Hertzian pressure distribution. And there is something strange here. It's a kind of what we normally call the pressure spike, and this behavior comes from, or it can be explained in the following way. It's a kind of continuity problem here. When you bring in lubricant here, if this is a line contact now, it's infinite into the screen here. You have there is a infinite long contact. So the lubricant can only move in the horizontal direction here. So you entrap some lubricant here at the inlet, you move it through the contact, and you squeeze it out here in the outlet. But remembering the lubrication fundamentals here, in the inlet you bring in lubricant here in a bigger gap here, but the pressure formed here, it wants to squeeze it back again. So you have the Couette flow, it wants to bring it in, the Poiseuille flow wants to squeeze it out. Here in the midsection, you only have the Couette flow because the pressure gradient is zero. And out in the outlet then instead, then both the Couette flow and the Poiseuille flow wants to squeeze it out from the contact. So of course the flow, the lubricant flow must be the same here, and everywhere in all the intersections of the contact here. So in order to keep the flow balance here, you must lower the film thickness here, because Poiseuille and Couette flow are helping each other. So for that reason, this gap must be smaller than the inlet gap. And nature is fantastic in that way. It actually it does this automatically, and in order to create this gap here, you must apply a local pressure here that makes this possible. So for that reason, this pressure spike occurs just here, where the surfaces are kind of rapidly deformed, or the film thickness is rapidly deformed here. So the explanation to the pressure spike and to why the minimum film thickness occur at the very edge of the contact is flow continuity, and together with the force equilibrium, of course. Those two are the natural laws that we always must follow here in mechanics. So a little bit about the figure I showed in the beginning then. In order to explain that, I must explain some interferometric measurement techniques here, which are used normally in order to study EHL. In a model contact or EHL, you form that by a ball and in contact with a glass disc. And on the glass disc, you put a half transparent or semi-transparent chromium layer, which is a beam splitter. So that means if you shine some light here through the glass, and then part of the light is reflected in that chromium layer, and part of the light is reflected in the ball. And since this distance is very small, it's about the same order of magnitude of visible light wavelengths, and so these two beams, they can interfere with each other, and if you do that, we have equipment to do that, and then you create a pattern like this. So this is, you recognize here that the contact, this is the Hertz contact zone, in this case a ball on a flat disc. So here in the center of the contact, the blue light interferes constructively, and that means and for that reason the blue color is much stronger than the other colors, and you see a blue part here. Then you can see some other, so each color actually is the same thickness of the lubricant film. So what you can see here, when you get some experience from this, you can see here that the film thickness is the thinnest actually here and here, and it's also very thin here along the rim of the contact. So the absolutely thinnest film in the EHL contact is formed along the edge of the Hertzian zone, and in here it's relatively flat. So it's the same in a circular contact, it's the same as in the line contact I showed, but in this case the absolutely smallest film or thinnest film is here and here. So that is the explanation to the beautiful or colorful picture here. And we can translate this colorful interferogram into film thickness maps. So this is what I said, and the flat part here where the film thickness is about the same, and along here the edge the film is the thinnest. And you can also compute what kind of pressure do you need in order to get that behavior, and then it looks like this. And you can see a small thing here, that is the pressure spike, or now it's a kind of pressure ridge, maybe we can call it. It goes around this contact here. So that's both a line contact and in this case a circular EHL contact. Okay, now I have tried to explain that there is a film formed, and the wedge mechanism is active here, but still it's a fluid. The oil or the lubricant is a fluid, so we must ask ourselves also, why isn't the lubricant just squeezed out from the contact when you have so extremely high pressures like gigapascals in the contact? So Then we have to take a look on viscosity here of a typical lubricant, a typical oil. If you measure the viscosity and measure the viscosity at different pressures, so in this case then pressures which are relevant for EHL like gigapascals, you can see that the viscosity may increase significantly. It's something like 5, 6, 7 orders of magnitude. That means that if it was a fluid at atmospheric pressure, up here at gigapascal pressures, it has some crazy numbers in viscosity, and that means it's almost like glass, or it's more like a solid than a fluid. And normally we use this expression to. This is very approximative, but it's a good way of thinking, a good way of explaining the influence of pressure on viscosity. So it's actually an exponential function here. So, and the alpha here determines how much the viscosity increases with pressure. So for typical mineral oils and synthetic lubricants, you end up with an alpha that is in the neighborhood here of 2 multiplied by 10 with the power minus 8. So putting the numbers in here, you will see that you get very big, large viscosities at pressures in a gigapascal range. If you multiply this number by gigapascal, you end up with a number like in this case 26. So E with the power 26, that's a lot. But if you take another fluid like water, the number is it's not that much smaller here, but putting it here, 4 E with the power 4 is a much smaller increase of the viscosity, and that's the explanation to why water isn't a very good lubricant for a ball bearing, for example. So it doesn't give you the same high viscosity. So having now this in the back of your head, knowing that the viscosity is extremely high, then you can compare an EHL contact with a football pitch. So if you increase everything to the size of a football pitch, and you take the same correlation between length of the contact and the thickness of the film. In a typical ball bearing, you may have the length of the contact is order of magnitude 1 millimeter, while the thickness of the film is something like 10 to 100 nanometers. Taking the same for a football pitch, which is around 100 meters long, then the film thickness is something like 1 to 10 millimeters. So if you put the lubricant here at the center spot and you try to squeeze it out, especially when you have a very, very high viscosity and you want to squeeze it out to the edge of the football pitch, you can understand that it's not very easy. So the solidified lubricant in the contact is very much trapped here. It doesn't have the time to be squeezed out during the short moment of time it takes for the roller to roll over the lubricant on the raceway. So that's the explanation to why the film can't escape from the contact. So finally, we are coming to the end of the video, and we're coming to the answer to the question that was raised in the beginning of the video. And the comparison between a non-conformal bearing like a ball bearing and a conformal surface type of bearing like the journal bearing. And why do they have about the same performance? Why do they have about the same load carrying capacity? Well, the answer is partly because a sufficiently thick film is formed in both cases. It is formed also in the non-conformal case. Even if it's thinner than in the journal bearing, it is formed and it fully separates the surfaces. But one should also remember that there is a rolling motion in this case, while it's a full sliding motion here. When you have full sliding, the asperities on one side has a big risk of colliding with asperities on the other surface, and then there is always a risk for lubricant film breakthrough when the film is thin. Well, that risk is much smaller in this case because the surfaces are following each other when they are rolling. So an asperity on one surface never collide with asperity on the other surface, and that's the explanation. If this bearing starts to slide, or if the ball starts to slide in contact with a raceway, then you have a problem, and the load carrying capacity is much poorer in that case. So that was a short introduction to elastohydrodynamic lubrication. In other videos, I will talk about how thick the film will be, and the parameters influencing that. I will also discuss friction in yet a second video. Thank you very much.